Hi everyone, welcome back to the lecture series on solid state chemistry. This is the sixth video on this topic. Today we will be discussing about plane dislocations, which is also known as surface dislocations. Let us see how does a plane dislocation or plane defect occur. When crystals or grains join together, the crystal lattice cannot be perfect and therefore a grain boundary may exist. At the atomic scale, each boundary is obvious as a discontinuity in the atomic packing. So, a plane defect results when line defects cluster together in a plane. Surface imperfections arise from a change in the stocking of atomic planes on or across a boundary. In geometric concept, surface imperfections are two-dimensional. The plane or surface dislocation can be classified into four: grain boundary, tilt boundary or lineage boundary, twin boundary, and stocking fault. So, a plane defect is classified as grain boundary, tilt boundary or lineage boundary, twin boundary, and stocking fault. Have a look at this picture. Here, you can see an orderly arrangement of lattice points or atoms here. As you see here, you can see an orderly arrangement. Then here also, as you see here, there is a perfect crystalline lattice arrangement, or atoms are arranged in a perfect manner. So you can see here, 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 these part you can see perfectly packed or positioned atoms. Now look at the boundaries. Here, look at the boundaries of each perfect arrangement. For example, here you can see the atoms are not following a perfect packing. Here, as you see here, this boundary. Okay, in these parts, the atoms are not following the perfect packing. So, we can see an area of imperfection that separate different crystals or grains of different orientation in a polycrystalline solid. So this perfect part and this perfect part, they lie in different orientation. So the area separating them can be considered as a boundary that separates these different grains or different crystals in a polycrystalline solid. So this type of defects are called grain boundaries, and grain boundaries are developing during the nucleation or crystallization process itself. This grain boundary is a two-dimensional imperfection. And during crystallization process, new crystals are formed from different parts and they are randomly oriented with respect to one another. As you see here, during the process of crystallization, new crystals are formed everywhere, and as you can see here, they are randomly oriented with respect to each other. Now a grain boundary, the boundary separating each of these crystals or these grains are called grain boundaries, and a grain boundary causes a discontinuity in the periodicity of the crystal lattice. As you see here, the occurrence of the grain boundary leads to a discontinuity in the periodicity of the crystal lattice of all these grains attached here. These grains, each of them grow bigger, grow closer, and they impinge each other. As you see here, they grow from different parts at a time and they impinge each other. The atoms held in between these grains, that is, the atoms in this boundary region, are attracted by crystals on either sides, and depending on the forces of attraction, these atoms occupy equilibrium position. So, atoms in this entire boundary region can be attracted by crystals or grains growing on different sides of this boundary, and depending on the force of attraction, these atoms in the boundary region, they attain equilibrium positions. This boundary region is called a crystal boundary or a grain boundary. Now let us summarize the general features about grain boundary. A grain boundary is a two-dimensional imperfection. During crystallization, new crystals form in different parts and they are randomly oriented with respect to one another. A grain boundary causes a discontinuity in the periodicity of the lattice of either grains. These grains or crystals, they grow and impinge on each other. Atoms held in between are attracted by crystals on either side, and depending on the forces, the atoms occupy equilibrium positions. This boundary region is called as a crystal boundary or a grain boundary. So what is a crystal boundary or a grain boundary? The boundary between two closely spaced crystals or grains that separate them is known as a grain boundary or a crystal boundary. In this figure, you can see differently oriented crystallites in a polycrystalline material. As you see here, you can see different parts of perfect packing, and then you can see the boundaries where the perfect packing is lost and there occur an imperfection, which is called as the grain boundary. This boundary separates this perfect packing from this perfect packing. Also here this boundary would separate this perfect packing or perfect crystal or grain from this grain. So you can see differently oriented crystallites in a polycrystalline material here. So this figure is a micrograph of a polycrystalline metal, and here you can see the occurrence of grain boundaries that separate different grains. Now let us see a video.
The two most common crystal structures in metals are body-centered cubic and face-centered cubic. These crystal structures grow uniformly in all directions within each developing crystal. As the metal cools, these crystals are confined by the adjacent developing crystals, forming grains. The line of intersection between grains is called a grain boundary. Because the grains form independently, their crystal structures develop tilted in various directions.
Hope this video helped you to understand how grain boundaries are formed during the nucleation or crystallization process. And these grain boundaries can also be called as a high angle boundary when the misorientation angle across the boundary are greater than or equal to 15 degrees. So when the angle between the misoriented crystals or grains are greater than or equal to 15 degrees, such grain boundaries can be called as high angle boundaries. In the case of a grain boundary, as you can see here, the orientation of the grains are different across a grain boundary. This change in orientation of grain across a boundary can be represented as a rotation. As you can see here, the orientation of this grain is different with respect to this one or this one across this grain boundary. Therefore, this change in orientation of grain across a boundary can be represented as a rotation. We can imagine this grain has been rotated in this direction to arrange it like this. Therefore, grain boundaries are rotation boundaries. Or in other words, grain on one side of the boundary is rotated with respect to grain on the other side of the boundary. Based on the magnitude of the angle of rotation, the grain boundaries can be classified as small angle boundary and large angle boundary. The angle of rotation is considered to be smaller than 5 degrees in the case of small angle boundary, and it is considered to be greater than 5 degrees in the case of large angle boundaries. The structure of the grain boundary depends on whether the angle of rotation is small or large. Small angle boundaries have lower energy than large angle boundaries. Grain boundary can be classified into two on the basis of the relationship of the rotation axis with respect to the boundary plane. The first one is tilt boundary, where the rotation axis is parallel to the boundary plane. In the case of twist boundary, the rotation axis is perpendicular to the boundary plane. Now let us see tilt boundary in detail. So in order to understand well about tilt boundaries, let us imagine the growth of two crystals or two grains from both sides of this particular grain boundary. So this is the grain boundary, and we are going to draw or represent the growth of two grains or two crystals on both sides of this grain boundary. So let us draw the lattice cells. Let us draw the crystal like this. So these are the lattice points. Okay, so we have one crystal going in this part, and now let us draw another crystal going on the other part of the grain boundary. So let it be like this. Okay, so we have unit cells of the crystal. So we have the unit cells of this crystal in this way. So this is the grain boundary, and now we can imagine this crystal being formed by rotating this crystal. Both of them have to be identical. So we can imagine this crystal or this particular grain is formed by rotating this crystal through a particular angle. Now let us imagine this crystal is formed by rotating this crystal in the clockwise direction along a particular axis called rotation axis. So it has to be rotated through an axis which is perpendicular to the plane of the screen. So we can say this is the rotation axis which is perpendicular to the plane of the screen. When we rotate this crystal through an angle, we can obtain this type of arrangement. Okay, so this is the rotation axis. Now this is the grain boundary or the boundary plane which also lies perpendicular to the plane of the screen. That is, it is a two-dimensional plane lying in this direction. Let me show it in another color. This is the two-dimensional plane that lies perpendicular to the plane of the screen. And as you can see here, the rotation axis is lying parallel to the boundary plane. So in this particular case, the rotation axis is lying parallel to the boundary plane. Okay, so when the rotation axis is lying parallel to the boundary plane, it is called as a tilt boundary. So in the case of a tilt boundary, the rotation axis lies parallel to the boundary plane. The scheme here represents the tilt boundary between two growing grains. Here the grains or crystals on either side are rotated with respect to each other such that the rotation axis lies in the grain boundary plane. So this is a plane, grain boundary plane passing through this part, and the rotation axis also lies in this plane. We had just discussed it before. And the rotation has to be made with respect to an angle theta in the clockwise direction in order to obtain this type of arrangement. If the rotation angle is small, that is less than 5 degrees, it is called as a small angle tilt boundary. The two crystals can be thought of independently rotated about the boundary plane on both sides. When both rotations are equal on both sides, that is, one rotation is exact half of the total rotation, it is called as a symmetric tilt boundary. That is, if theta is the total angle of this complete rotation, this rotation has to be theta by 2, and this rotation has also to be theta by 2. Such tilt boundaries can be called as a symmetric tilt boundary. As you see here, there are some planes that end up in between. As you can see here, this plane, this ends up here. And in the case of this crystal also, this plane ends up here. But this one grows continuously until this point and it ends up here. Similarly, you can see there are planes that end up towards the boundary plane or the grain boundary plane. These planes ending here corresponds to edge dislocation. That is, a vertical boundary can be considered as a set of parallel edge dislocation lying along the grain boundary. Now this tilt boundary can be considered as a set of parallel edge dislocations lying along the grain boundary. Now let us see the relationship between tilt axis and the Burgers vector. So here you can see some planes are abruptly ending here that correspond to an edge dislocation. So there will be associated Burgers vector. Due to the presence of this edge dislocations, there will be an associated Burgers vector. In this particular case, the Burgers vector would correspond to this distance, this unit cell distance, or this unit cell distance in this direction would corresponds to the Burgers vector. And now let us see the distance between two nearby edge dislocation. For example, this one ends here, this one ends here. So this distance can be represented by a small letter d. This is Burgers vector, the magnitude is small letter b, and this distance between nearby edge dislocations correspond to small letter d. So in this schematic representation you can see two grains growing together, grain 1 and grain 2, and this is the boundary, the grain boundary, and you can see the presence of edge dislocation. So a tilt boundary can be called as a low angle boundary when the orientation difference between two neighboring crystals is less than 5 degrees. The disruption in the boundary is not so severe as in the high angle boundary. Actually, a low angle tilt boundary is composed of edge dislocation lying one above the other. The angle or tilt will be given by sin theta by 2 is equal to b by 2d, where b is the Burgers vector, the magnitude of the Burgers vector, and d is the average vertical distance between neighboring edge dislocations. As you can see here, the growth of two grains or two crystals, and they get combined. So a grain boundary will be formed in between these two growing grains or crystals. As you can see here, when they grow together, these edge dislocations, they combine together to form parallelly placed edge dislocation towards the grain boundary. This boundary is known as a tilt boundary. Let us see what are twin boundaries. For that, let us consider twin boundary in the case of a cubic close-packed structure. As we know, the arrangement of planes in a cubic close-packed structure is in the sequence ABC, 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 like that. So this is the arrangement in the case of a perfect close-packed structure. Now let us see what happens in the case of a crystal containing twin boundary. Cubic close packing that contains a twin boundary. So the packing is like A, B, C, A, B, C. This part goes perfect. Now let us see what happens here. As you can see here, this arrangement is different. So this is the plane above which the arrangement corresponds to that of cubic close packing arrangement, a perfect arrangement, and below that the arrangement has been changed. So let us see. If we consider this as a mirror plane, this plane as a mirror plane, look at the sequencing above this mirror plane and below this mirror plane. You can see here it is B, C, A, B, C. Here also B, C, A, B, C. So you can see here this B here has been reflected here. Okay, similarly this C here has been reflected here. This A here has been reflected here. This B is reflected here, and this C is reflected to this point. And above there will be a normal sequencing again A, B, C, that A is reflected back here. So we can say this part below the mirror plane is a mirror image of the crystal above the mirror plane. Okay, this part below the mirror plane is a mirror image of the part above the mirror plane. So this mirror plane can also be called as a twin plane. If the upper one, the upper sequencing or the upper crystal is taken as the original crystal, then the lower one is the mirror image of the upper crystal, or it can be considered as a twin. Okay, so this plane is considered as a twin plane. Here, a new sequence is created below the twin plane, which is like a mirror image of the sequence on the other side of the twin plane. And here the orientation also gets changed. The orientation of the new sequence is different from the original one. The two orientations above and below the twin plane are related as mirror reflections. The orientation of the crystals above the mirror plane and below the mirror plane, or above the twin plane and below the twin plane, are related as mirror reflections or mirror images. So a twin boundary can be defined as a boundary in a crystal such that crystals on both sides are mirror images of each other. As you can see here, if the atomic arrangement on one side of a boundary is a mirror reflection of the arrangement on the other side, then it is called as a twin boundary. Here we can see the occurrence of two twin boundaries. This one is a twin boundary and this one is also a twin boundary. So if we consider this as the original crystal, then here we see its mirror image. So this plane is called as a twin boundary. Similarly, this part is the mirror image of this part. So hence this becomes again a twin boundary. So we can conclude a twin boundary can be defined as a boundary in a crystal such that crystals on both sides are mirror images of each other. A twin boundary can be defined as a boundary in a crystal such that crystals on both sides are mirror images of each other. Twin boundaries occur in pair and hence are called twin boundaries. Such type of boundaries occur in pair and hence are called as twin boundaries. Orientation of atomic arrangement of one crystal is different from the other. The orientation of planes changes at the twin boundaries. The orientation will be different because one crystal is the mirror reflection of the other crystal. So the orientation of one crystal will be different with respect to the other crystal. And the orientation of the planes changes at the twin boundary that separates the two different crystals. At another boundary, the original structure is restored back. The region between the pair of boundaries is called as the twinned region. The region between the pair of boundaries is called as the twinned region. These boundaries can easily be identified under an optical microscope. If you view such crystals through an optical microscope, we can clearly see the occurrence of twin boundaries. So here you can see, if we consider this as the original structure, then we have the reflection here. This part is a reflection of this crystal. So when we check, we can see the original crystal has been regenerated here. So this is the twinned region. This region is called as the twinned region that separates two perfect parts of the, or two original parts of the crystal. So this is the twinned region and these are the twin boundaries. Stoking fault is another type of plane dislocation. Let us see in detail about stoking faults now. A stoking fault is a fault in the stoking sequence of planes in a crystal. So a stoking fault is a fault or deviation in the stoking sequence of a planes in a crystal. In order to understand more about stoking faults, let us consider the stoking series in the case of a cubic close packed crystal. Here on the left side you can see a perfect CCP arrangement where the sequencing is like ABC, 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 ABC. And in the right side we can see a CCP structure with a faulted sequencing. So it is similar to the same type of arrangement ABC, AB, but as you can see here one of the C plane is missing. The rest is ABC, ABC. So from the crystal lattice one of the C plane is missing in the case of a faulted CCP arrangement. Now let us have a closer look into this sequencing. As you can see here, the part above the missed plane, that is this part ABC and this one ABC. They follow perfect CCP arrangement with ABC, ABC packing. And below also, as you can see here, it follows ABC packing corresponding to perfect CCP arrangement. But look at this local area where the C plane is missing, or the area of fault or the area of dislocation. We can see only AB type of arrangement. That would correspond to an HCP arrangement. So in this local area of the defect, the perfect CCP arrangement is lost and rather an HCP arrangement can be observed. Above and below the missing planes are perfect CCP arrangements. The local area of dislocation, the sequence is AB type, that is, it's like an HCP arrangement. This may occur when a crystal is growing and planes get added to the crystal system. As the entire C plane is missing here, it is a two-dimensional defect. As entire plane is missing, that the dislocation extends to a plane. So it is a two-dimensional defect. Here, the orientation of the crystal does not change across the fault plane. As you can see, the orientation is maintained. The orientation is not changing with respect to the faulty plane. That is, there is no change in the orientation of the crystal across the stocking fault. The difference between these two crystals above the fault and below the fault are restricted only to the stocking difference. Whenever the stocking of atomic planes is not in a proper sequence throughout the crystal, the fault caused is known as the stocking fault. For example, the stocking fault as we considered here, the sequencing in a CCP crystal may be described as ABC, ABC, ABC type arrangement. However, the stocking fault may change to the sequence of ABC, AB, AB, ABC. The region in which the stocking fault occurs, that is the AB-AB region, forms a thin region and it becomes an HCP type of arrangement. This thin region is a surface imperfection and is called as a stocking fault. So here you have a schematic representation, and the left side you can see ABC, ABC, ABC type packing corresponding to perfect CCP arrangement, whereas here in the right side you can see ABC, then one of the C plane is missing from there, again another C plane is missing here. So after the CCP arrangement of ABC, it becomes AB, AB, and then again back to the normal ABC type of arrangement. So this area AB, AB, that would correspond to an HCP arrangement. So this area, this region would correspond to a plane defect called stocking fault that originates from a difference in arrangement of, difference in sequencing of planes in this particular part of the crystal and is called as stocking fault. So this was all about plane defects. We have discussed about grain boundaries, tilt boundaries, twist boundaries, twin boundaries and stocking faults. Hope you got a clear idea. Thank you.